And the question says, identifying the reagents shown in bold in the following equations as nucleophiles or electrophiles. So we are supposed to tell which is a nucleophile or which is an electrophile. Well, unfortunately everything is in bold, so nothing can be said about this. But yes, in this case, if you see, well, this is a nucleophile. Wow, this is a nucleophile? Yes. Why? Because it can donate a lone pair of electrons. Cyanide also is a nucleophile. Why? Because it can donate a lone pair of electrons. Acyl cation CH3CO+. It has two contributing structures. One is this and another is CH3CO+, like this. First one is more contributing, second one is less, but nonetheless both of them very much are there. Now what is this? This is an electrophile. Why? It is a plus charge. It is electron deficient, as you can see. So it can accept a lone pair of electrons. So these two are nucleophiles and this is an electrophile. That's it. That's it. As simple as this. Classify the following reactions in one of the reaction types studied in this unit. Okay. Now, how do we classify organic reactions? Well, they could be classified as substitution if one species comes in and the other one goes out, or elimination if one molecule breaks up into maybe two or more parts, or addition if two or more parts or species join to give you one single unit. So it's either addition or elimination or substitution. One thing. So in that sense, if you see, there are two species, right? HS minus moves in, it gets attached as SH, and Br minus moves out. What is that? One species comes in, the other one goes out. This is a classic case of, yes, you have got it, it is substitution. And not just this, if you look at this species here, HS minus, is it an electrophile or a nucleophile? It has lone pairs, it is trying to donate lone pairs. Yes, it is a nucleophile indeed. So this first reaction is nucleophilic substitution. It has nucleophiles, nucleophilic, and it undergoes substitution. So this is substitution. What about B? Well, you have two molecules here and these two molecules combine to give you one molecule. Beautiful. So this is an addition reaction. Yes, it is an addition reaction. Anything else? Is it nucleophilic, electrophilic? What kind? You are having HCl. Now HCl actually gives you H+. And what is H+? Is it electron rich or electron deficient? Of course, H+ is always electron deficient. It is plus, right? So it is electrophilic addition. H+, this is obtained from any acid. You have HCl, H2SO4, any acid. H+ is an electrophile. So you have electrophilic addition. C part. Two molecules are giving you, well, three molecules. What is this? If you just care to note, OH minus has become HOH. HO minus and H plus will give you HOH. So it appears as if this OH minus, when it has changed to H2O, H2O can be imagined as OH minus plus H plus, just for the purpose of imagining. So in case I write this H2O as H plus and OH minus, these OH minus ions can just be cancelled in imagination, not actually. And I'll get this molecule is breaking up as ethene plus H plus Br minus. Oh my God, what is this? It means that one of the molecules, CH3CH2Br, ethyl bromide, has broken away into two species, ethene plus Br minus, or maybe H plus also separately. A single species is breaking up into multiple species. My dears, this is a classic case of elimination reaction. Yes. So this is elimination. Don't we call elimination nucleophilic or electrophilic? No, we just call elimination elimination. That's it. Fine. And the last and the least, well, what do you have? You have HCl like HBr again. So this is electrophilic addition. Just wait and watch. You have CH3 whole thrice C, CH2OH, fine. And some reaction, and you find that OH has been lost and Br walks in, and you get H2O. So ultimately what is happening? This OH group is being replaced by a Br group, and something else is also happening within the molecule. Essentially, this is a substitution reaction. It is a substitution reaction. Now, just at the primary stage, it may not be very comfortable for you to figure out which kind of substitution is that. Nucleophilic, electrophilic, whatever, but ultimately, see, Br minus has moved in. HBr has broken as H plus and Br minus. And since this Br minus moves in, and Br minus would function as a nucleophile, yes. So people normally call it even nucleophilic substitution. Is it nucleophilic substitution? Yes, very much. It is nucleophilic substitution. What is the relationship between the members of the following pair of structures? Okay. Are they structural or geometrical isomers or resonance contributors? Let's take a look. The first one, they are definitely isomers, yes. Because you can see 1, 2, 3. This is pentane 3-one and this is 1, 2, 3, 4, 5. This is pentane 2-one. Pentane 3-one and pentane 2-one. They are position isomers. So there are structural, yes, and honestly they are position isomers. Okay, what about these? DD on the opposite side, DD on the same side. You have 1, 2 dideuteroethene, 1, 2 dideuteroethene, but in this case, deuteriums are on the opposite side. This is trans. On the same side, this is cis. So they are geometrical isomers. Yes, indeed. And the last one, HCOHOH. Okay, very interesting. And then you have another one. Now, honestly, one should draw lone pairs also properly. That's very important. What has happened is this electron cloud has jumped here, and you get this. If you just notice in both these cases, the difference is only in the location of an electron cloud. All the atoms are exactly in the same position as such. So at best, they can be called resonance contributors. So are they resonance contributors? Yes, they are resonance contributors. Why? Actually, there's no significant difference. It is just that only pi electron cloud is differing. And if two structures differ only in the location of pi electron cloud, they are resonance contributors. There it is. For the following bond cleavages, use curved arrow notation to show the electronic flow. Lovely. And classify each of them as homolysis or heterolysis. Identify the reactive intermediates produced as free radicals, carbocations or carbanions. This is a very valuable, very easy but a very valuable question because it gives you great insights. Now you have methyl peroxide, CH3OOCH3. Lovely. One must never draw without proper electron cloud. It has to be like this. I'll just eating away electron clouds is never any good person's intention. It's never a welcome activity. Right. Now, if you notice, what happens is one electron goes here and the other one goes here. More style, you should draw it like this. So the curved arrow must begin from the middle. It must end on oxygen atoms because one electron each. See, it is homolysis. one bond contains 2 electrons, and from these 2 electrons, one goes here and one goes here. So this is homolysis. Yes, this is homolysis. Why? Homo means similar. So the bond breaks up in an equal way, and this gets 1 electron and the other one also gets 1 electron. Anything else? You get free radicals? Yes, you get free radicals. Done? Done. B part. Well, what happens? It seems that there is a minus charge here. Okay, and how does that minus charge arrive there? Actually, you know what happens is this. There is CH3, CO, CH3, right? If you remove H plus, because see, this OH minus has become H2O. What does that mean? It means that one H plus has been taken away and one lone pair is here. Right. So what has happened is, it is like this. Electron from OH minus, electron pair has been donated. This bond breaks up in a heterolytic fashion. It has given away both the electrons to carbon, and that is why carbon has acquired a minus charge and a lone pair. Sometimes there are people who say that when you have already put a minus charge, why do you show the lone pair? Minus charge is just the formal charge. Lone pairs must be written very clearly and explicitly, and formal charge, it does not indicate a lone pair, it just indicates formal charge minus. Many a times, negative formal charge is possible even without a lone pair of electrons. So, lone pair should be very clearly identified and charges should be shown separately. This does not mean an extra lone pair, please note. This is it. So, do you see? This is the area when we are showing the bond breaking like this. This is heterolysis. And we have obtained an carb anion. Is carbanion? Yeah. Tertiary butyl bromide. It dissociates to give you tertiary butyl cation and bromide ion. How does this happen? See, this bond breaks. Wow, like this? Yes, like this. Let me show you lone pairs clearly. There were 3 electron pairs and now there are 4. This is heterolysis? Yes. And by this, you get a carbocation. There's a plus charge, so it's a cation, carbocation. Benzene ring plus electrophile is giving you a rhenium ion. Fine. How are the electrons moving? What is happening? Most interesting. See, this is the way we show it. Okay. This pi bond has been donated. Yes, indeed. And what has happened? You can imagine it like this. This is just imagination, but very useful one. You have a benzene ring? Yes. Just imagine that it breaks in this fashion. Wow. So what I get? I would get, is this heterolysis? Yes. And then you find that this E plus gets this donation. So what do you get? Then you get this species. This one. So actually, the way you show it is this, but you should always imagine. I am showing you imagination bubble also. We don't write this, but this is actually what should be imagined. Pi bond jumps on one side. There is a heterolytic fission of pi bond. This was heterolytic fission of sigma. This is now heterolytic fission of pi. Plus and minus. Minus goes to donation. This is what you get. There we are. Right? So this is, well, homolysis? No, it is heterolysis once again. And we get a carbocation. A very different one, but yes, we get a carbocation in this again. Explain the terms inductive and electromeric effects. Which electron displacement effect explains the following orders of acidity of carboxylic acids. Now, second part, let me answer first. You find that both these effects are explained very well by inductive effect. How is it? I'll just show you. The logical portion I'll just answer first. You have CCl3 COOH. Now please note, this has withdrawn electrons. Oxygen withdraws from hydrogen, fine. And you find that this group, these chlorines, since these chlorines are taking electron cloud away from carbon and it is withdrawing from here. If you have electron withdrawing groups which are taking electrons away from acidic hydrogen, then acidic strength increases. So if you compare this with another molecule which has only 2 Cl atoms, obviously 2 Cl atoms do not have the same withdrawing power as 3 together. So they can withdraw only as much. So acidic strength would not be as great. And if you have only 1 Cl atom, the withdrawing power would be still less. So as the number of -I groups Cl atoms increases, a negative inductive effect of -I effect increases, and that increases the acidic strength of these carboxylic acids. Oh wow, that is the case? Yes, that is the case. Opposite is the case here. You have COOH, wonderful, and then you have CH2, wonderful, and then you have CH3. So it should be written as, you know, something like CHHCH3. Fine. If I replace these hydrogens by more and more methyl groups are electron releasing groups. So I'll get HCCH3CH3 COOH, which is this. And if I write all 3 methyl groups, I'll get this CH3 C CH3 CH3 COOH. So please note 1, 2 and 3 methyl groups. Methyl groups are +I groups. They're electron releasing groups. So if they release electrons, please note this is the acidic hydrogen. If electron releasing groups are attached to the other part of the acidic hydrogen, then they decrease the acidic strength. So if they keep on releasing, 1 methyl releases a little, 2 methyls release more, 3 methyls release still more. You'll find acidic strength would decrease because of +I effect. So this is -I of Cl and this is +I of methyl groups, which explains this order of acidity. As for what exactly is inductive or electromeric effect, take a look at the theory. I'll just move away from screen so that you can enjoy the entire theory properly. I'll keep speaking. If you just look at -I effect, permanent displacement of sigma electron cloud in one direction because of attachment to groups of different electronegativity, that, my dear, is called inductive effect. If a species withdraws electrons, it is said to show -I. If it releases electrons, it is said to show +I effect. And this is how, one would represent the answer. You can take a screenshot in case you need, and you have this. And then the second part, electromeric effect. What is electromeric effect? Temporary displacement of pi electron clouds. If pi electron clouds jump on one side simply because of interaction with another species, another molecule, another ion which is approaching them, that is called electromeric effect. Pi bonds may jump on one side, then they may come back. It's a temporary effect, right? And again, if electrons move away, it is +E. If the electrons move towards a certain species, that is called -E effect. Give a brief description of the principles of following techniques. Taking an example in each case, you have crystallization, distillation and chromatography. Now, this is a purely theoretical question and I'm offering you theoretical answers, clean, nicely written answers for this. Again, you would need to take these down and, well, if there is an exam, you're supposed to reproduce them. So this is the theory for you as for your board syllabus. You can take screenshots as required or note down the answers. Crystallization, this is distillation. and then you have chromatography. We are not going in repetition of theory, so it's a neatly written answer for you. Chromatography also can be classified as, well, column chromatography and thin layer chromatography. One should have both, and this is a description of both for you. Describe the method which can be used to separate two compounds with different solubilities in a solvent. Now, in a solvent, I think there is no S required here. Simple correction, but many times students find this very difficult to comprehend. So let me support this with an example also along with the explanation. Let us say we have two substances. Let's say we have something like NaCl, which is sodium chloride. The sodium chloride or salt, common salt, water soluble, it's very much water soluble. And let us say it has a solubility of 200 grams per liter. This is not the exact figure. I'm just saying a random round figure so that it feels good and it's easy to calculate, and it's a close figure. It's a good example. And on the other hand, let's take something like, say, magnesium sulfate. And say, although magnesium sulfate is reasonably happily soluble in water, let me assume that, say, around 40 grams per liter of magnesium sulfate dissolves in water. So these are the solubilities. So they have different solubilities. Yes, they have different solubilities, and they have been mixed. Now, had I had something like NaCl and something which is water insoluble, it would have been very simple. I just add water, NaCl dissolves, and the other substance does not dissolve. I can filter and separate. The problem is both of them are water soluble. If I have them mixed, and now I'm asked, okay, use water to separate them out. How do I do this? Well, there is a beautiful method. And what is that method? Let me relate that to you. Say, these are the solubilities, and I am given a mixture of NaCl and MgSO4. And say, for example, and please note, there is no necessity that the mixture would have NaCl and MgSO4 in this ratio only. It could be any amount. Say the mixture contains 200 grams of NaCl and say it has 80 grams of magnesium sulfate. Anything of that kind. Any stupidity. Fine. Now what do I do? Well, I know very well that for dissolving magnesium sulfate, I need how much? 40 grams per liter. That means 1 liter I would need for dissolving 40 grams. If I have 80 grams, let me say I need how much? 2 liters. So what do? I keep on adding water to this mixture and keep on adding water till both the salts dissolve. And in this case, I would need, say, initially 2 liters of water. For 40 grams, I needed 1 liter. So for 80 grams, I need 2 liters. But now you will say that for 200 grams, you needed 1 liter. Fine. So now you have 2 liters, right? So in 2 liters, 400 grams of common salt, NaCl can dissolve? Yes, they can. But I just have 200 grams. If I have less, will they dissolve? Yes. If I have more, then they will not dissolve, right? So I have a solution. What did I do? I had a mixture of solid NaCl and MgSO4, and I kept on adding water and water and water till both of these dissolved. And now I just used 200 liters of water, sorry, 2 liters of water, and both of them dissolved perfectly. What do I do now? Let me start boiling this. If I start boiling this, what happens? Well, water evaporates, and as water evaporates, and say this 2 liters of water, if I boil and reduce it to 1 liter, what happens? From 2 liters, within this 2 liter, I had 200 grams NaCl and 80 grams of MgSO4 dissolved. Yes. Now, when the water volume has been reduced to only 1 liter, what happens? You can see very clearly that in 1 liter, 200 grams of NaCl, which is more soluble, can still dissolve. So yes, I still have 200 grams of NaCl very much. So I have 200 grams of NaCl, right? But in 1 liter, only 40 grams can dissolve. Yes, and I have 80 grams. So what happens? So 40 grams of MgSO4, they will remain in the solution, yes, but 40 grams of MgSO4, what happens to them? They crystallize out. It crystallizes out. You get solid crystals of MgSO4 and there is no NaCl. It's pure lovely crystals of MgSO4 crystallizing out. Why? Because within 1 liter of solvent or water, not more than 40 grams of MgSO4 can remain. So, the remaining 40 grams out of 80, 40 has to remain. Remaining 40 has to come out. So, from a mixture of NaCl and MgSO4, I have got 40 grams of pure MgSO4 separated. Right? Right. This is a process which is called fractional crystallization. Now, just let's take a look at this in a more formal way. It's written here. Fractional crystallization. It is crystallization, not distillation, of course. That is wrongly written here. I'll just move aside. Take a look. Fractional crystallization can be used to separate these two compounds with different solubilities in solvent S. You find that first you take a powdered mixture, you add solvent, keep on stirring it, warming it till you find that the solid mixture totally dissolves in the liquid and you have a saturated solution. Fine. Now you boil that solution. As you boil the solution, you find, and you can filter it also at the same time, after some time, you would find that, like in our example, MgSO4 had crystallized out. The less soluble salt will begin to crystallize out. The less soluble salt begins to crystallize out. So you can collect those crystals very nicely. Now you might say that, sir, you separated 40 grams of MgSO4, fine. But then there was some NaCl and there was some MgSO4 still remaining in the solution, very much. What happens if you further crystallize that? If you further boil the solution, now you find that since the solution, in our previous example, the solution did contain 200 grams of NaCl and 40 grams of MgSO4. If you boil it further, you would find some salt will also crystallize and some MgSO4 will also crystallize. It would not be any further possible to separate these by this method. This much you have got pure, and that is the limitation of fractional crystallization. So this technique is useful only when there is a significant difference in the solubilities. Please note, that would be a very key and important factor. But nonetheless, as far as the method goes very well. First, you boil, then the less soluble salt crystallizes out, you separate it, and then the classical method says once the less soluble salt is separated out, you further boil it so that the more soluble salt also crystallizes out. But please don't forget, the last installment, the more soluble salt, when it crystallizes out, it will definitely contain some traces of the less soluble salt. This is not clearly mentioned here, but that is always the case for fractional crystallization. This was fractional crystallization for you. What is the difference between distillation under reduced pressure, and steam distillation? Now, what is distillation, dear? In distillation, what happens is you boil a given liquid mixture, and if you have a component in the mixture which is volatile, it evaporates away, which you can condense, of course, cool, condense and separate out, and the remaining portion is either non-volatile or something which has much higher boiling point, which does not boil easily. So separation method, in case you have a mixture containing components with significant difference in boiling points, then the process of separation is distillation. What about distillation under reduced pressure? If you have a component which begins to decompose as you boil it, like you say if you have something like glycerol. Now, glycerol, if you start boiling it around 320 degrees Celsius, the boiling point, but if you heat it that much, then it also begins to decompose. So we need to actually reduce the external pressure, and if you reduce the external pressure, the most beautiful part is boiling point gets reduced. The same glycerol can be boiled at barely around 180 degrees Celsius and it evaporates off without actual decomposition. So this is distillation under reduced pressure. It is specifically used for the components which decompose on boiling or on strong heating. Steam distillation is a different ball game altogether. When you are distilling or distilling under reduced pressure, you could be heating it directly. But steam distillation means that the source of heat is steam. Whatever mixture has to be distilled, you pass steam. As steam is passed, steam condenses, it releases a lot of heat, and that heat vaporizes the remaining portion of the initial mixture or the distillant, as we call it. As it boils along with water vapors. So you have a mixture of substance vapors as well as water vapors. Both of these are condensed, collected in a separating funnel, and since they are mutually immiscible, they are immiscible with water, one of the components, like for example water, it settles at the bottom, the other component remains at the top, and they can be easily separated by a separating funnel or something like that. And this is how we actually separate them. So this is steam distillation for you. I'll just move aside so that you can see the theory also and take notes or snapshots, whatever required. This is a comparison between distillation under reduced pressure, and steam distillation. Discuss the chemistry of Sinus test. Now, Sinus test is very interesting. It is used for detection of nitrogen, sulfur, halogens or phosphorus within organic compounds. How do we actually perform Sinus test? We take a sample of any given organic compound, we add it in a small tube, and then we add metallic sodium. Metallic sodium, yes, sodium is very reactive. We add them, melt and fuse them together. Molten sodium, because it's very, very reactive, it destroys the given organic compound, takes out all the nitrogen, phosphorus, sulfur, halogens, and forms different compounds, and those different compounds or species can be specifically tested using specific reagents, and this overall process is called Sinus test. Take a look. If you have nitrogen, and organic compounds obviously possess carbon, so carbon, nitrogen and metallic sodium, they all combine and you get the most poisonous and dangerous sodium cyanide. Oh my God. And if you have sulfur, it forms Na2S. If you have halogens, they form NaX. One thing which is not mentioned here is a rare exception, and that is if you have nitrogen and sulfur both, then you don't get either NaCN or Na2S, you get NaSCN. They combine together to give you thiocyanate ion. This is also, if you have only nitrogen, other than, see, organic compound will always have hydrogen and carbon. But if you have only nitrogen, you get sodium cyanide. If you have only sulfur, you get sodium sulfide. If you have both nitrogen and sulfur, then you get sodium thiocyanate. Okay. And how are these species tested? But this is the real fun part. So step 1, organic compound, sodium, heat, fuse, and then extract it with water. Add the thing to a solution of to water, cold water, so that that solution contains either one or more of these species. And now this solution, after filtering, will be tested. How exactly? Let's see. After adding the fused mixture in water and filtering, you have a solution. This solution is divided into 3-4 different parts. In the first part, you add a little tiny bit of ferrous sulfate. Ferrous sulfate, and acidify it also because you have sodium, etc. The solution might be alkaline. So before that, you add some dilute sulfuric acid, make the solution acidic, and along with add ferrous sulfate. You will find, in case cyanide ion is present, cyanide could be dangerous, but adding ferrous locks it up as ferrocyanide ions, FeCN6 4-, and these are non-poisonous. These ferrocyanide ions, they don't have a very significant color, but now just add a drop of ferric ions. First you added ferrous sulfate, now just add a drop of ferric ion. Okay. Otherwise ferrous is already present. Add some quantity of an oxidizing agent like a drop of nitric acid, concentrated nitric acid for example. And even if some ferrous gets oxidized to ferric, you find that this ferric with this ferrocyanide would create a very beautiful dark blue precipitate of Prussian blue. Ferriferrocyanide? Yes, ferriferrocyanide. And this blue precipitate, a dark blue precipitate, the so-called Prussian blue precipitate, confirms the presence of nitrogen in the original organic compound as per the Sinus test. Let me move aside, just take a look at the reaction written here. You could note that down. This is the Sinus Test for you for nitrogen. What about sulfur? Sulfur would be forming sulphide ions. Sulphide ions can be tested with sodium nitroprusside. Sodium nitroprusside, yes, perfectly. And what is sodium nitroprusside? This is nitroprusside ion. It's faint brownish yellowish solution. If you add sulphide to this, suddenly it becomes violet coloration. Even a very small quantity of sulphides are present, still it's a very clear, distinct test. A very distinct violet coloration gives you a confirmation that sulphide is present, which confirms the presence of sulfur in the original organic compound. What about halogens? Halogens they're very easy, they'll form halides, like chloride, bromide, iodide. You add silver nitrate, first acidify them and then add silver nitrate. You get either AgCl or AgBr or AgI as precipitates and then add aqueous ammonia. If AgCl is present, AgCl will dissolve completely in aqueous ammonia, giving you a colorless solution. AgBr dissolves partially with difficulty if you have dilute ammonia especially, and AgI fails to dissolve in dilute ammonia absolutely. But nonetheless, this is again a beautiful confirmation and distinction as well for chloride, bromide as well as iodide. These are Lysine tests for for nitrogen, sulfur and halides. Dumas method and Geldahl's method, both are the methods for estimation of nitrogen in a given organic compound. And especially you would find that this nitrogen estimation is valuable. When exactly? It is valuable when we are estimating proteins. But then for the time being, what are the methods? In Dumas method, which is an older method of course, you heat a given sample of organic compound to around 800 to 900 degrees Celsius. So Dumas method, you heat it to 800 to 900 degrees Celsius, while in this case it is just 360 to 410 degrees Celsius. So this is one point of distinction. This is Dumas method, this is Geldahl's. I'm just mapping it here. This requires heating with oxygen, and this requires heating with concentrated sulfuric acid. But this will destroy the compound. Yes, it will destroy the compound. Who cares? We are just analyzing the substance. So if you're heating any substance desperately with oxygen, what happens? This is organic compound, it would burn. So nitrogen is oxidized to N2. All nitrogen is converted to N2. And in this case, all nitrogen in organic compound is converted to NH4 plus. Okay. So Dumas method, you take the substance, you burn it with oxygen, and the nitrogen which is collected, you get CO2, H2O and nitrogen. CO2 and H2O are absorbed by KOH and dehydrating agents. The only nitrogen which remains, that is estimated that this is the amount of nitrogen remaining, and that gives you the idea of percentage of nitrogen in the given organic compound. Simple method, quick method. Dumas method takes only a few minutes if a setup is very ready. Geldahl's method takes roughly an hour or so. So it's a longer method, but again it is supposed to be safe, because in Dumas method a lot of fire etc. is burned because you are burning it. It is safer, nothing drastic as such. But Geldahl's method uses poisonous catalysts, which is bad. Dumas method does not involve any poisonous catalyst. So in that sense, yes, there is a significant difference. What happens here? Take organic compound, heat it with concentrated sulfuric acid, and that heating actually oxidizes the organic compound and breaks it down, and all the nitrogen is converted to ammonium. Within the organic compound, if there is a nitrogen atom, it is converted to NH4 plus. Then you add NaOH, excess of NaOH to this mixture, boil it. So this NH4 plus, if you add OH minus and boil, it is released as ammonia. And this ammonia gas which is liberated is then trapped into a known quantity of acid. Okay, say for example, so many milliequivalents of acid is present and you add ammonia. So some part of acid is titrated, it is neutralized, it is removed, and the remaining part of acid is now back titrated with a standard solution of NaOH so that we can get an idea of how much of ammonia is present. I've been quick, yes, because again this is just a comparison, we are not explaining Dumas and Dumas method, but in a sense the principle, the difference in the principles is nitrogen is converted to N2 and nitrogen is converted to ammonia. This is a major difference. Discuss the principle of estimation of halogens, sulfur and phosphorus present in the organic compound. Now, if you want to estimate how much of quantity of these is present, see, halogens are oxidized and separated as halides. They are precipitated as AgX, and mass of AgX can be measured. You can calculate moles of AgX, and from there you can get moles of X, and accordingly percentage of halogen in the original organic compound. A very standard regular principle for estimation of halides. Sulfur is converted to, sulfur is oxidized to sulfate. Please note, we are not trying to identify the presence of sulfur. That is done in the Sinus Test, etc. That is qualitative method. This is quantitative. What is the percentage of sulfur? So sulfur is oxidized to sulfate, and then you add barium ions. So this sulfur is precipitated entirely as barium sulfate, and mass of barium sulfate can be experimentally measured. This will give you mass of BaSO4. From there you can calculate moles of BaSO4, and from there you can estimate, of course, everything, that, the moles of sulfur, etc. What about phosphorus? Phosphorus is oxidized to phosphate, and this phosphate can be actually identified or isolated in many ways, but typically it is precipitated in the form of, yes, you add ammonium molybdate here. And you get a precipitate, a yellow colored precipitate of ammonium phosphomolybdate. This is very drastic. You get NH4 whole thrice, phosphomolybdate, PMO12O40, like this. You can measure it out, you can filter the precipitate, wash it, clean it, measure its mass, and from there you can find the mass of phosphorus, and that will give you an estimate of amount of phosphorus present in the organic compound. There are more methods, but these are very standard methods for estimation of halides, sulfur and phosphorus in the organic compound. Explain the principle of paper chromatography. Now you will find theirs. Chromatography is based on the principle of selective adsorption. What does that mean? Different solvents have different tendencies of adsorption on a given piece of paper, and this is something which matters. In paper, I've written all the details here. As you have a mixture of substances and then you have a solvent which carries both these substances, or 2 or 3 or 4 or whatever is the mixture, then if a substance has a bigger tendency to get adsorbed, it gets stuck, it remains there. The one which actually is not very well adsorbed, it moves again, it moves up along with the solvent which is seeping through, which is washing it up, and this is how you separate them. So brief outline, the details are written out here, and as we are discussing just the solutions, I'm just going to move aside and you can take a look at the answer. This is how you would represent this. Could take a screenshot and add this to your stock. Why is nitric acid added to sodium extract before adding silver nitrate to testing halogens? Now this is very necessary because see, sodium extract makes the solution alkaline. You have unreacted sodium, and this unreacted sodium reacts with water to produce NaOH. And if you are adding silver nitrate, in case NaOH is present, you would get a black precipitate of silver oxide. This NaOH would produce a black precipitate of silver oxide with silver nitrate. And this is something which you don't want. So what do? If you don't want this, then this NaOH is destroyed by nitric acid. And why only nitric acid? Because nitric acid itself gives only nitrate ions, and nitrate ions do not produce any precipitate with silver ions, which are going to be added just after this. Hence, nitric acid. Explain the reason for fusion of an organic compound with metallic sodium for testing nitrogen, sulfur and halogens. Metallic sodium is one of the most powerful reducing agent, and if you heat it, if you fuse it, it becomes very, very reactive. So this metallic sodium, it releases electrons, and these electrons can be taken up by nitrogen, sulfur or halogens because they are also electronegative atoms. In that process, they are reduced to the minimum state. So because sodium is sufficiently reactive, it can break down a given organic compound, it can totally reduce nitrogen, sulfur and halogens to their minimum states, and they can be extracted separately. That is why exactly molten sodium fusion is used. Name a suitable technique for separation of components from a mixture of calcium sulfate and camphor. Now, camphor is a volatile substance, right? So, a very simple technique is sublimation. What do? You just take calcium sulfate. Calcium sulfate is absolutely non-volatile. If you heat it, it won't evaporate and it won't even decompose easily. On the other hand, if you heat camphor, camphor would suddenly sublime. So, just heat it. If you have, say, if you have a mixture of these two, what do? Just heat it and keep an inverted funnel over this. Cover it with an inverted funnel like this. You will find as camphor sublimes, camphor vapors will tend to deposit here. And if you are afraid of losing camphor, you can just cap it also. So, yeah, your camphor gets deposited here and calcium sulfate remains in the plate. It's a beautiful separation. That's it. Well, let's take a look at this very interesting question which says, explain why an organic liquid vaporizes at a temperature below its boiling point in its steam distillation. Before we actually attempt this question, I just want to revise a piece of theory for you. What is boiling point mathematically? Well, the temperature at which vapor pressure of liquid becomes equal to 1 atmosphere, then temperature is called boiling point. Okay, fine. And when does this mixture boil? This mixture boils, first of all, please understand, vapor pressure of mixture, because you have liquids which are immiscible with water, the vapor pressure of mixture is equal to vapor pressure of water plus vapor pressure of liquid. You have to add them up, right? By common sense. If you have immiscible liquids, you add up individual vapor pressures and you get vapor pressure of the mixture. Fine. And I would say that this mixture is boiling. I am defining the boiling point of mixture as, I would say this mixture is boiling if mixture boils, if vapor pressure of mixture is equal to 1 atmosphere. To the temperature at which vapor pressure of mixture is 1 atmosphere, I would say that the mixture is boiling. And if mixture is boiling, every component in the mixture is boiling, people assume that. If that is the case, my dear, now vapor pressure of mixture, please note, is vapor pressure of water plus vapor pressure of liquid. The vapor pressure of water plus vapor pressure of liquid is equal to 1 atmosphere if the mixture boils. Fine. If the combined vapor pressure is 1 atmosphere, that means vapor pressure of liquid is 1 minus vapor pressure of water, which is less than 1 atmosphere. Vapor pressure of water would be some value, right? So, if I subtract something positive from 1, I would get a number less than 1. So, that means vapor pressure of liquid has to be less than 1 atmosphere. when vapor pressure of liquid is 1 atmosphere, that temperature is the boiling point. And at this temperature, vapor pressure of liquid is less than 1 atmosphere. That means this temperature is less than the boiling point of the liquid. Right? This is what is being said. Why organic liquid vaporizes temperature below its boiling point? So you can see temperature of liquid is less than its normal boiling point and still the mixture is boiling. And this is the beauty of steam distillation. Will CCl give white precipitate of AgCl with AgNO3? No. Why? Simply because AgCl gives white precipitate, AgCl's white precipitate is obtained on adding silver nitrate only with ionic chlorides. CCl4 has pure covalent bonds. They do not release Cl minus ions. And since they don't release Cl minus ions, nothing of that sort happens. Why is a solution of potassium hydroxide used to absorb carbon dioxide evolved during estimation of carbon present in an organic compound? That's not very difficult. Actually, KOH is a base and CO2 is acidic. KOH completely reacts with CO2. KOH completely reacts with CO2 to form potassium carbonate. So it takes away, it traps all the carbon dioxide, it very effectively removes all the carbon dioxide. And that is why people love it, and it is used in removal of carbon dioxide from from estimations. So when carbon dioxide is passed through potash bulbs, this is also called potash. So when it is passed through potash bulbs, it is absorbed, and the increase in mass of potash bulbs would give you the mass of carbon dioxide as per this reaction. Why is it necessary to use acetic acid and not sulfuric acid for acidification of sodium extract for testing sulfur by lead acetate test? Please note that if you are using lead acetate test, that means you are using lead ions. And lead ions, if you add acetate ions, no precipitate. But if you add sulfate ions from H2SO4, they will give you extra PbSO4 as precipitate. You were trying to estimate sulfur. You converted all the sulfur to sulfate. And now, out of stupidity, if you add extra sulfate in sulfuric acid, you will get more sulfur than it is already there, because you have added extra sulfur in the form of sulfuric acid. So that is something you must not do. Right? That's why. An organic compound contains 69% carbon and 4.8% hydrogen. So you have carbon and hydrogen, 69 and 4.8%. Now please note, this is not adding up to 100% nonetheless. And the remainder being oxygen. So the remainder is oxygen, even more dangerous. Very interesting and very good. Let's see what luck has in store for us. So total is 100 grams. In case, let us assume we have 100 grams of organic compound, this much is carbon and hydrogen. How much is oxygen? That would be 100 minus, add this, that is 73.8. How much is that? Well, 26.2 grams. It becomes 26.2 grams, right? This is mass. Calculate the masses of carbon dioxide and water produced. Okay. When 0.2 grams of this substance is subjected to complete combustion, oh my God. Now, you would find that we have mass. If total 100 grams of compound, I have so much of carbon and hydrogen. I could always calculate, instead of 100 grams, had I had only 0.2 grams of this substance, what would have been the mass of carbon or hydrogen here? Could I have done that? Yes, let's try. Can we take moles? Yes. 69 by 12. 4.8 by 1, 26.2 by 16. I don't think we need oxygen, but still, just for namesake, I've done that. So many moles of carbon atoms. These are moles of atoms. Let me make it clear. I'm not asked the empirical formula, etc. So let me not bother. Let me see, had I had 100 grams, these many moles of carbon would have been there. So moles of CO2 would have been how many? Same moles, 69 by 12, right? And moles of H2O would have been, now H2O contains 2 hydrogens. So one hydrogen, I mean, if you have 4.8 moles of hydrogen, you would get 4.8 upon 2 moles of water. Okay, so these many moles of water and these many moles of carbon dioxide. Fine. And we wanted the masses. So let's calculate mass, that's not a problem. This is mass of CO2 would have been 69 by 12 into 44. Why? Because molar mass of CO2 is 44. Molar mass of water is 18. So I would have 4.8 by 2 is 2.4. I'll just divide this. 2.4 into 18 grams per mole. So many grams of CO2 and H2O had I started with 100 grams of mixture. But I don't have 100 grams. Instead of 100, I just have 0.2 grams. So this is simple ratio and proportion. 100 grams of organic compound gives how many grams? This dirt, 69 by 12 into 44 grams CO2. So 0.2 grams of organic compound will give how much? 0.2 into, this is 3, this is 11, 69 into 11 upon 3. The whole damn thing divided by 100. This into this by this. So many grams of what? Of CO2. So mass of CO2 would be, let's look at this. This is 0.2 into 23 into 11 by 100. That makes it 0.23. Whatever this multiplication comes out to be, we can quickly do that and get at. How much is 11 to the 33? 3 11 to the 22 and 325 into 2. This is 506, 3 decimals. I get 0.506 grams. This is just calculation, I just strike it out. I get 0.506 grams of CO2. Same way, we have mass of water. How much would that be? 2.4 into 18 into 0.2 upon 100. You repeat that thing. Instead of 100 grams, take 0.2 grams. This is the mass you would obtain. And that would come out to be, well, 18 4s are 72, 18 2s are 36, and 43. Fine. So this is 0.432 into 0.2. This is 0.0864 grams. You will get 0.0864 grams of water. This is the answer. Now the question says a sample of 0.5 grams of an organic compound was treated according to Geldahl's method. Okay. The ammonia evolved. Now let's keep noting the data. I think that will be useful. Let's not worry too much about the word Geldahl. I mean, we have essentially 0.5 grams of an organic compound. Lovely. And what happens in Geldahl's method? All the nitrogen is converted to ammonia. So I have all nitrogen to ammonia. And this ammonia which was evolved it was absorbed in what? 50 ml of 0.5 molar H2SO4. Fantastic. So what happens? This ammonia totally reacts away with the sulfuric acid, and this is usually in excess. Fine. The residual acid, there is extra acid which remains, and that required how much? It required 60 ml of 0.5 molar NaOH for neutralization. There are two bases, and together they are eating away this acid. Find the percentage of nitrogen in the compound. Very simple. How do we solve this? Total milliequivalents of acid is equal to total milliequivalents of base. So milliequivalents of ammonia plus milliequivalents of NaOH is equal to milliequivalents of H2SO4. This is the basic concept. Milliequivalents of base total is equal to milliequivalents of acid. How do we find this? Now, milliequivalents of ammonia is millimoles of ammonia into 1. Why? There is 1, N factor is 1. Plus milliequivalents of NaOH. Multiply them. 16 to 0.5. That makes it 30. And NaOH, this is 30 millimoles, and equivalence factor. Now millimoles into N factor is equal to milliequivalents. We know that, right? So into 1. This is equal to milliequivalents of sulfuric acid. 50 into 0.5, and for H2SO4 N factor is 2. It is not 1. So 50 into 0.5 into 2. Oh wow. How much is this? This is 50, this is 30. So millimoles of ammonia comes out to be 50 minus 30, which is 20. We have 20 millimoles of ammonia. That means this corresponds to 20 millimoles of nitrogen atoms, because one ammonia contains 1 nitrogen atom. So 20 millimoles of nitrogen atoms. And if you have 20 millimoles, my dear, of nitrogen atoms, what is the mass? So mass of N atoms is 20 millimoles into 14 grams per mole, which is 280 milligrams. So percentage of nitrogen, we have 0.5 grams, 500 milligrams. So 280 by 500 into 100, which is 56%. So we have 56% nitrogen by mass in the given organic compound. 0.378 grams of an organic chloro compound. Okay. So let's note 0.378 grams of an organic chloro compound gave a lot of dirty numbers. 0.574 grams of AgCl in Carius estimation. Students sometimes are afraid, wow, Carius, Jaldal. Skip the names. Ultimately, it is just principle of atomic conservation. So many grams of organic compound gave so much of AgCl. Calculate the percentage of chlorine present in compound. Oh my God, that's very simple. You have mass of AgCl, fine. Therefore, moles of AgCl will be 0.574 upon molar mass of AgCl. Now, silver is 108, chlorine is 35.5, add a 143.5. 143. So many moles of AgCl, or 574 upon 143.5 millimoles. Just to make the numbers look more humane. So many millimoles of AgCl, and this is equal to millimoles of chloride ions, or even chlorine atoms. Electrons are practically massless. So we have mass of chlorine. Therefore, mass of Cl atoms is 574 upon 143.5 into 35.5 milligrams. There were millimoles, multiply them by atomic mass, so you get mass of chlorine atoms. Fine. And we needed percentage of chlorine. So percentage of chlorine is mass of chlorine by mass of organic compound into 100. Now mass of chlorine is how much? That dirty number. It is in milligrams. Fine. So 574 into 35.5 divided by 143.5. So many milligrams. Divided by how much? 378 milligrams. Milligrams. Grams have to be converted to milligrams into 100. I just have to solve this dirty number and I get the answer. Calculation, as you know, is always a problem for many of the students. I will give you, of course, an accurate answer. You can look at the answer and get that, calculate that. I can also give you rough calculation, how to quickly calculate and estimate a reasonable answer. That trick also I'll tell you. Let's try estimating this. Before we calculate, let me give you official answer for those who are not interested in calculation, only in the answer. It's around 37%, 37.57%. Sorry. And now people may say, how exactly you got that? For them, I have this calculation method which I am trying to elucidate. I'll need some space, I'll erase out some portion of the answer. See, watch here. Try to cancel as many things as you can. And well, I have 574, that's fine. I have 355, then I have 378, these are close numbers. And then I have 1435. I have just deleted one decimal. Let me see how this works. Now, first of all, this 355, 378, they appear close to me. I'm just first trying to figure out, can I cancel some numbers? Let me see, 350. Now, if I have 350, 350 into 4 gives me 1400. Yes, 1400. Now, 355 into 4 will give me 1420. And I have 1435. Now, 1420, 1435, give me a break. It is roughly 4 times. Just let me do it 4 times. Oh my God, so drastic? Yes, actually it should have been 1420. So I have actually reduced denominator slightly, but nonetheless, see here. If I have reduced this number, I can increase this slightly. Instead of 378, would I be allowed to make it at least 400? Oh, that's a bit too much. But I could actually make it at least 380 or a little more. Okay, agreed. Of 380 and 574, they again don't look like very beautiful numbers, but I'm just trying to figure out if something nice can be done about them. I could just increase them slightly. I could make it 600 and I could make this 400. If I could just do that, just see how does it work out. Well, this is 3 and this is 2. This is roughly 3 by 8. 3 by 8 is 37.5, 0.37. So I'll get 37.5%. By this approximation also I get 37.5%. Accurate answer is 37.57%. Pretty close. I think I'm good. There we are. In the estimation of sulfur by Carius method, okay, 0.468 grams of organic compound offered 0.668 grams of barium sulfate. How dumb. Find the percentage of sulfur. Nothing can be easier. This is the mass of barium sulfate. The moles of barium sulfate, how many? This is mass of barium sulfate upon molar mass of barium sulfate, which is 0.668 by barium is 137, sulfate is 96, 233 grams per mole. How much is that? Ugly, whatever it is. I get some number. Fine. So many moles of barium sulfate. Therefore, this is equal to moles of sulfur atoms. Because one barium sulfate contains only one sulfur atom. Therefore, mass of sulfur atoms is 0.668 upon 233 into 32 grams. That's it. That's it. And percentage of sulfur in the organic compound is mass of sulfur upon mass of organic compound into 100. Common sense. Mass of sulfur is 0.668 into 32 divided by 233 divided by this gandh 0.468 into 100. Oh my God. How much does that come out to be? Let's calculate. 668 by 468. Fanciful. Into 32 by 233. Fine. How much does that give me? Let's, well, give it a shot. If you are accurate enough, you'll get 19.6%. Of course, into 100. This gives you a value of 19.6%. And again, if you are keen to learn how do you calculate, I'm always up for a calculation trick. I'll just do an approximate math and show you how that calculation might be carried out roughly. You have 668 by 468 into 32 by 233. Well, now if I just begin my manipulations, let me see which other cancellations I might do. The moment I notice the 68, that 68 gives me 67.77. I always get a feeling the 68 is like 200 by 3. Okay. So 600 plus 200 by 3. That makes it how much? 600, 2000 by 3. So this number is how much? 2000 upon 3 divided by, this would be 1000 by 3? No, that is 200 plus 400, 412, 1400. Yeah, into 32 by 233. We'll see this also. We'll find out something for this. Now by 3 goes off, this goes off. This number becomes a lot cleaner. This is 10 by 7. This number is approximately 10 by 7 into 32 by 233. Now 233 is a real ugly number. Could I make it 240? Well, nobody would mind. 0 cancels away. 3s and 4s. Okay, so what do I have? Into 100 of course survives. So I have 4 by 21 into 100. Now just see, had it been like, 40 by 20 into 10, it would have been 20%. Now denominator is not 20, it is 21, slightly less than 20%. And we have the answer as 19.6%. That's reasonable, very close. In the organic compound CH2 double bond CH, CH2, CH2, C triple bond CH, the pair of hybridized orbitals involved in the formation of C2-C3 bond is, now C2-C3 bond, first of all we have to name this also, and that is 1, 2, 3, that is how we should name it, and it would be like 1, 2, 3, 4. So this is C2 and C3. Why this side? Alkene and alkyne. Ene is alphabetically before than ine. This gets a preference. Okay. So this carbon CH2, CH, CH2. This is 2, 3. This carbon is sp2. This carbon is sp2 and this carbon is sp3. So which orbitals are involved? sp2, sp3. sp2, sp3. Is C the answer? Yes, you can see. C is the answer. In the Sinus test for nitrogen in an organic compound, the Prussian blue color is obtained due to formation of. Now what exactly is formed? Which is Prussian blue? Fe4, FeCN6 whole thrice. You just know what is Prussian blue. That's it. It's as simple as that. Which of these carbocations is most stable? Well, how do you compare stabilities? Primary, secondary, tertiary. Stability goes on increasing. This is simply primary. This is primary. This is tertiary. And this is, you can see here, secondary only. Most stable is tertiary. Why? Because carbon is connected to 3,3 methyl groups. Yes, indeed. So each of these methyl groups exerts a plus I, and there's also hyperconjugation which stabilizes the carbocation, and that's why the stability here. The best and latest technique for isolation, purification and separation of organic compounds is crystallization, distillation and sublimation are ancient. The latest is chromatography. Yes, stylish, fanciful and very accurate. The reaction CH3CH2I ethyl iodide plus KOH gives you ethyl alcohol plus Ki. What is happening? What is happening is OH minus ions are coming in and they are kicking this I minus out. Wow. OH minus is a nucleophile? Yes, it's a nucleophile. So it is nucleophilic. One species I minus is replaced by another species OH minus. It is substitution. So what we are witnessing here is a nucleophilic substitution reaction. B is the answer. So dears, this was the long chapter of some basic principles and techniques for organic compounds. Now this is a chapter which is very crucial when it comes to forming fundamentals of your organic chemistry. I must say that I'm not very happy with the way in which it has been presented in the NCERT. I don't have a very high opinion about it. Too many concepts just packed into one in a very unstructured and systematic fashion. But nonetheless, I'm quite sure that this discussion of NCERT questions will be very helpful. In case you have problems with this chapter, we have a fantastic, initial, can say course, Basic Organic Nomenclature, and which is followed by General Organic Chemistry. If you have to appreciate the basics of these, then always come and attend my courses on this on Vyas app. So again, is it an advertisement? It's a plain statement of fact. I don't say this very often with all my courses, but then since studying this from NCERT may not be a very sublime experience for you in case you want to understand organic chemistry, joining these two courses on Vyas app would be very useful for you for being able to appreciate organic chemistry properly from its basics. Come, explore and learn. And by the way, even if you don't join any of those courses, that's perfectly okay. These solutions also would be helpful in understanding and clearing many concepts. I have tried my level best for that. Good luck.